Let's discuss equilibrium. At this point in the semester, we're used to thinking as if reactions only occur in one direction. For example, hydrogen combining with iodine to produce HI. We've alluded to the idea that the reaction might also occur in the reverse reaction. HI decomposes into hydrogen gas and iodine gas. Some reactions can progress in the forward and reverse reaction directions simultaneously. And in that case, we replace our unidirectional arrows with an equilibrium arrow, which communicates that at the same time that hydrogen and iodine are combining to form HI, the HI is decomposing into iodine gas and hydrogen gas. So let's say that we did a reaction with hydrogen and iodine. Just before the reaction begins, our reaction mixture might look like this. Our shaded spheres and blobs are iodine. Our unshaded spheres and blobs are hydrogen. When our reaction begins, reactants are consumed and products are formed, so that 17 seconds after the reaction begins, our mixture might look like this. We've consumed some of our iodine and hydrogen molecules to produce some HI. If we were to graph the changes in concentrations of each of these substances with time, it might look like this. Time is on our x-axis, concentration is on our y-axis. We can see that as time progresses, the concentration of each of my reactants is decreasing. At the same time, the concentration of my product is increasing. At a certain point, the products can react to reform some of the reactants, and our reaction mixture might look like this at 32 seconds. We've made more product molecules, and we've used up more of our reactant molecules. Let's look at the reaction mixture 15 seconds later. If you look closely, you'll notice that the number of product molecules is the same in both pictures. The same is true for your reactant molecules. So something has happened between 32 seconds and 47 seconds. What's happened is that equilibrium has been reached. Equilibrium is where the forward and reverse reactions are occurring simultaneously at the same rate. So that at the same time, at the same rate that hydrogen and iodine are combining to form HI, the HI is decomposing into iodine and hydrogen. This means that the concentrations of the reactants and the products are remaining constant with passing time. If we look back at our graph, our lines have gone flat. There is no longer any change in concentration with passing time for our reactants or our products. So it's important to note that this is not a static point. This is a dynamic process. It's just communicating that at the same rate that hydrogen and iodine are combining to form HI, HI is reacting to reform the iodine and the hydrogen, so that the concentrations of your reactants and products are remaining constant with passing time. It's important to note that while the concentrations of reactants and products are constant at equilibrium, they're not necessarily equal. Some reactions are product favored, which means that at equilibrium, there's a higher concentration of products than reactants. Some reactions are reactant favored, which means that at equilibrium, the concentration of reactants is greater than the concentration of the products. The measure of whether the product favoredness or the reactant favoredness of a reaction is given by the equilibrium constant, which is represented by capital K. The equilibrium constant gives the ratio of the products to the reactants at equilibrium. So let's say, for example, A and B are in equilibrium with C and D. Our lowercase italicized letters in front are our coefficients in our balanced chemical equation. So our equilibrium constant is given by the concentration of product C raised to its coefficient times the concentration of D raised to its coefficient, divided by the concentration of A raised to its coefficient times the concentration of B raised to its coefficient. The brackets mean concentration of. It's important to note that pure solids and pure liquids are left of an equilibrium constant expression because those concentrations won't change with time. Your equilibrium constant is always going to be products over reactants, which means that you can use that to establish the reactant favoredness or the product favoredness of a reaction. If it is a product favored equilibrium, that means you're going to have more products at equilibrium, which appear on the top of this expression, which means that your equilibrium constant is going to be greater than 1. If it's a reactant favored equilibrium, that means you're going to have a higher concentration of your reactants at equilibrium than your products, which means that your equilibrium constant is going to be less than 1.